I'm going to tell you a little bit about this ongoing field of implantable brain-computer interfaces and a little bit about our ongoing research called BrainGate. As you just heard, I spent some of my time as a neurointensivist helping patients with life-threatening injuries or illnesses of the nervous system. And when I'm in the neuro ICU, I have many of the exact same thoughts as I do when I'm in the lab. If I see somebody who has just had a spinal cord injury or a stroke, I'd like to be able to assure that person that they're going to be able to move again tomorrow. If I see somebody who was able to walk and able to speak yesterday without any difficulty, but just had a brainstem stroke and became locked in, unable to move and unable to speak, I'd like to be able to say, I'm sorry that this happened, but you're going to be able to communicate easily again tomorrow. And if I meet somebody with ALS, either in the clinic or in their home, I'd like to be able to assure them that they will never lose the ability to communicate. What I'll show you in a moment is that this field of implanted brain-computer interfaces and our ongoing BrainGate research is on the way to being able to make these very statements. Any brain-computer interface that you hear about, whether it's the one I'll tell you about momentarily or any others, has three major components: a neural sensor, a decoder, and some action that BCI does. For the sensor, this is a device that's placed somewhere on or in the brain that records neural activity, records a particular signal from any number of areas. Once that signal is in hand, it then goes into the black box. And that black box is really the magic of computational neuroscience, and of course these days, ML or artificial intelligence, being able to decode the intent of somebody's movement. For example, somebody with spinal cord injury attempting to move their hand, if we can decode that signal from the brain and we can hold on to that signal, then we may be able to send it to the next phase, which is some sort of action. And it's really in this black box where much of the innovation that I'll describe is ongoing. That action, of course, for somebody who's unable to move could be regaining control over a computer cursor, regaining full control over their laptop or tablet. For somebody unable to speak, to just think about speaking and to be able to use that neural activity to once again have audible conversational output. So let me introduce you to a gentleman. He had a cervical spinal cord injury. He has no use of his hands. He has a little bit of use, the proximal part of his arms, and he's looking on the top at a Windows PC and a Kindle reader, and below it is an iPad. If you look over to the right at those screen grabs, there's another little window in there. That's a graphical user interface, what we call BG or BrainGate Home. And that innovation is going to allow him, just by thinking about the movement of his own hand, to do what many people here are doing every day, using their own hand to grab any number of devices, to activate one device on their desktop, and then to move to another one, whether it be a coffee cup or another computer. Here, he's thinking about using his own hand. A cursor will move very quickly. He's thinking about making various grasps. He's therefore instructed the cursor to move from the Kindle reader down to the iPad to do what's most important, which of course, to launch GarageBand. And with that GarageBand, which will move forward, there it is, he's going to continue. Just a second, may need a little help from the team in the back. There we go. So he's going to keep going with GarageBand, and what he's doing is actually fairly complicated. He's thinking about which instrument he wants to select. He's thinking about what he wants to do, where he wants to place that beat. It's a lot of thought, it's a lot of precision, but it's actually really easy. It's quite intuitive. It's intuitive because we're recording the signals from his motor cortex that allow him just to think about moving his own hand, much as some people here today may be writing, taking notes, not really thinking about it at all. If we can harness these neural activities and we can convert them to real-time output, we can restore intuitive, rapid, and effective control over external devices. Here's the same gentleman. He's unable to open and close his own hand, but we've connected the implanted BCI to this soft robotic glove that's allowing him to open and close his own hand. And here, while he has some ability to flex and extend about the elbow, he can't open and close his own hand. But here we've, in some ways, reconnected brain to limb. He's able to think about opening and closing his hand. He's able to grab this yellow block in what is a very standard kind of neurological and physical medicine assessment, and able to do so quite easily and readily. Another method of communication is handwriting. The green squiggles that you're seeing are what I would call a neural trajectory. They are the output of the neural activity as a gentleman who's unable to move his own arm or hand thinks about drawing those letters in cursive. That handwriting's actually better than mine. But it's not the fastest way to decode neural activity. A more modern way to do that would be to take all of that neural activity in the upper left. It's really the language of the nervous system, the pattern of those action potentials from dozens of neurons firing away, put it through a recurrent neural network, pick up the signature associated with any intended letter to write, and either output that directly or to use any of the language models that we're all familiar with and to update that predicted letter or that predicted word. So here's a gentleman, ignore the big box on the top of his head, that has and will continue to go away. He's unable to move his arm or hand, and he's been asked the question that's on the screen, and he's going to begin to write, or attempt to write, or intend to write one letter at a time. And you'll see the output in real time of his full vocabulary answer to this question. He's able to write anything he'd like, could output that at about 90 characters per minute. It's about 94% accurate out of the box. Put that through a language model, it gets up to 99% plus accuracy. Decoding intended speech. Speech is, of course, one of the most rapid ways for communication, and if we could restore that speed, that accuracy, and that fluency, it could be of tremendous help to any number of people with communication impairments. Here, same concept, take the neural activity, run it through a recurrent neural network, and then subsequently put that through a language model. The gentleman who you're seeing has ALS, or Lou Gehrig's disease. You will in a moment hear his voice, his attempted output, and what you'll see on the screen is our decoding of the neural activity and the conversion of that neural activity into words. Note the text that's on the top, that what you're seeing is the second day of use of this investigational BrainGate implanted neural interface. First things that he shares with us is that sense of humor, making sure that he knows that we know that this is all working as planned on day 2. And as we continue, he's going to continue to say what he'd like, and we're going to decode that strictly from the neural activity. And you can hear the difference between what's appearing on the screen and what we might be able to discern from his audible output.
I have been waiting for this for a long time.
This will continue for just a moment. What I'd point out is this video is edited just a little bit, skipped a couple of sentences. The second sentence that he spoke on the second day was, "I'm looking for a cheetah." As a computational neuroscientist, as a neuroengineer, that to me has got to be a decoding error. There's no way that his second sentence is, "I'm looking for a cheetah," except for the fact that his 4-year-old daughter had just walked in the room dressed as a cheetah. And this was the first time in years that she, at 4 years old, was able to hear and really hear his voice. In fact, the voice that you heard coming out of the computer was a deep fake for good of his own pre-ALS voice, and the rest of this conversation is his ability to interact with her verbally for one of the first times. So as we think about these implanted BCIs, I'm hopeful that we're going to be able to make these statements that are there on the screen. How do we get there? Well, we continue the academic research of showing what's possible, setting the bar ever higher and higher. Some of these innovations that I've described today are either patents that have been issued or are under review, with opportunities for licensing and creating further products. Our Center for Neurotechnology and Neurorecovery is really experienced in designing both pilot and pivotal trials in these implanted and other neurotechnologies, helping any number of the companies that are out there to make sure they can do the best possible clinical trials to ensure the safety and hopefully feasibility and ultimately efficacy of their devices. And Mass General Brigham was also recently wonderfully able to convene the Implantable BCI Collaborative Community, the first FDA participating collaborative community in the clinical neurosciences, establishing an official chartered pre-competitive space for the many companies in the space, as well as the academics, the researchers, the engineers, people with lived experience of paralysis, ethicists, and other federal agencies to gather to begin to address some of the many challenges of getting this important field from where it is today to be able to make these devices available to the people who will benefit from them. With that, I thank you very much, and I look forward to meeting some of you later today.